Now, let's go to flexural strengthening of reinforced concrete beam. As mentioned in this lecture, we will design FRP for beam, we will design FRP for moment and shear of the beam. And in the next part, we will see the column. So as you can see clearly, loading the beam, there is moment over here. Due to that moment, at the tensile point, we'll see some cracks and we'll see the failure of the beam. This failure clearly indicates that there are not sufficient reinforcement at the bottom to provide the tensile strengths for the beam. Ignore this bit of failure. This is due to the loading position, but this crack clearly is a tensile crack. Yeah, see, it looks like a happy face and there is tension over there. So if I design some FRP to be added at the bottom of this to help the reinforcement bar to provide the tension, we're successful. Look at this beam in a structure which has been clearly overloaded and it has bended. With FRP, we could have prevented this. Now, the retrofitting, as we discussed, is needed whenever my resistance of that section is lower than my applied load. I have a lot of elephants in my room, but a very small section, so I need to retrofit. As we mentioned, FRP only takes the tensile force, so we will only apply it to the base which are tensile. This is a beam with fixed ends, so you can imagine the happy face goes a little bit higher. So I have tension here, I have tension in the middle, and I have tension at the other end. So reinforcement with FRP, reinforcement with FRP, reinforcement with FRP. Anywhere that I have tension due to the loading, I will apply the FRP. Pay attention to the direction that this guy is applying it. For a flexural bending, it follows the longitudinal reinforcement of the section because those guys have the duty to carry the tensile force. After the FRP is applied, now I have solved my problem. This situation changes to this situation. My resistance is higher than my applied. My structure is stronger than 100 elephants on top of it. Before we carry on, similar to that the bonding factor and the strength of FRP, we have to get familiar with 4 important factors, which continuously we will see it in our formulations. One of them is the partial factor of FRP for material. One of them is the partial factor gamma RD of FRP for resistance modes, which we will discuss what it means. Another one is an environmental factor, and one of the other ones is the maximum FRP tensile strength. Do you remember we discussed about the relationship between stress, strain, and elastic modulus? Now I have the elastic modulus, I have the strength of my FRP, so let's see what happens to the tensile strain of my FRP. So the partial factor of FRP for material depends on whether you're considering serviceability limit state, ultimate limit state, and whether you're considering debonding happening or debonding prevented. Depending on all of these, there will be a factor. As you can see, it's 1 or 1.10 or 1.20 or 1.50. Depending on the design, either your client or the situation will tell you what is the factor, or the factory will tell you, or you can find it from the code. So you will always be given what is that partial factor. Regarding the partial factor which is related to resistance mode, again, if you're designing it for shear or torsion is 1.2. If you're designing it for bending or a combination of bending and axial load, which happens in columns, the resisting factor is 1. If you're dealing it for a column which needs additional confinement, is then 1.1. So looking at the situation, you know why you are designing it. Currently we are discussing about flexural strengthening, so I know that we're dealing with bending. So whenever I see this sign, I know it's 1. Look at this. Depending on which material you're using and whether you're internal or external, the environmental factor is generally smaller when you're applying it internally, because anyhow the FRP is less exposed to environmental factors which are like moisture, alkali environment, which whenever the pH is greater than 7, you have an alkali environment like seawater. which happens a lot, extreme temperatures, thermal cycles, freeze and heat cycles, UV light. If any of these are happening, usually is externally. So the environmental factor is a little bit lower. But if it happens internally, you're safer. So the environmental factor is a little bit higher. So it's just saving you from the environment. And as we discussed, the tensile strain. So the tensile strain is a minimum of any of these two. Whatever the value of this is, or whatever the value of this is, the smaller value will be selected. If you look at this, sigma FDD, didn't you see that FDD in the debonding strength? Yes. So if I calculate that strength that I have, which in this case was FDD mode 2, so the rupture happening due to the crack inside the section, which that was the long formula, if I just divide it simply by elastic modulus, I get the strain. Wasn't this the relationship that we always had? Stress over strain equals elastic modulus. So now I have calculated the new debonding strength factor for FRP, the strength of the FRP under mode 2. I have the elastic modulus of my FRP, so I just simply divide them. I have the strain due to that, the maximum FRP strength at failure due to intermediate debonding starting from vertical crack in concrete. Your strain is either this value or this other value. This other value, as you can see, the environmental factor plays in it. And this is a partial factor, which depends on some criteria. As you can see, there's a value, and this is the maximum FRP strain at failure due to rupture of FRP system. This is the strain that we discussed in the beginning. This is given by the factory. The factory has done some tests, like the tensile test that we saw in the beginning. It draws some graphs and says, okay, this is the maximum FRP. At this strain, my FRP will rupture. Now, if I have a value here and I have a value here, I'll take the smaller one to be on the safe side. So again, one comes from the factory and I just apply some environmental factors and some partial factors to it. The other one comes from considering the debonding, which was mode 2. Whichever is smaller, I'll take that and I'll carry on in my calculations. Now, let's look at the calculation bits. Again, we have some simple, let's say, assumptions that we always did in ultimate limit state. Hopefully you remember them. If not, please read these. These are not related to this course that much. It's just the basis of designing a section. Now, two important factors is that the flexural failure occurs when one of the following conditions is met. So either this case or this case, I will have a flexural failure in my concrete. And as you can see, both of them relates to the strain. So either my concrete compressive strength is reached. Again, concrete has very good compressive resistance. So we're looking at the concrete compressive strain. We have reached to that strain and my concrete has blown up. So I have failed. According to Eurocode 2, generally concrete has a strain of, let's say, 0.35%. Now, or on the tensile side, I have reached the maximum FRP tensile strain. At point that I reached that, my tension member, which is FRP, has failed and my section has failed. So because we have a composite material which is concrete and is resisting in compression, either that strain has reached and my material has failed, or my FRP has reached this strain and it has failed. Just few minutes ago, we were talking about how to calculate the strain of FRP. And we said it's a minimum of either this value, which comes from the factory and we just apply a partial factor and an environmental factor, or it comes from this formula, which I calculate the strain of my FRP due to the debonding occurring due to the vertical cracks in the concrete, and I just simply divide it by the elastic modulus of FRP. So I once calculate this, I calculate this, the minimum value of these two will give me the maximum FRP tensile strength. Whenever I pass this in my section due to the loading, or I pass this in my section due to the loading, either in compression or tension, my section will fail. I'm sure you all remember this analysis of section. Hopefully you remember. If you can't remember it, I strongly suggest that you have a look at any of these references that we have in this lecture or from your previous studies in your undergrads to remember how we analyzed a concrete section. So this is a cross-sectional area of my concrete. I have let's say compressive steel on the top, AS2, tensile steel at the bottom, AS1. I know that my member will be loaded in a way that I will have tension at the bottom and compression on the top. Because I have tension at the bottom, I have added FRP at the bottom, and that will have an AF, which is the area of my FRP. And then the other properties like the height, the D, the cover in the top, cover at the bottom, width of my FRP, and the width of the section. This is the strain diagram, and this is the stress diagram. Hopefully you still remember how to draw these. If not, please review what you were doing. And we were always drawing this, if you remember, which there was the strain of concrete in the compression and the strain of steel in the tension. Now that I have added FRP, the strain of my FRP is much higher than the strain of my steel. So you see, we have moved from here, zoop, all the way to here. Now we discussed that the failure happens either in concrete or in FRP. So we called it region 1, reaching maximum FRP tensile strain, so reaching this guy and failure happens, or we called it region 2, reaching maximum concrete compressive strain at this point. The compressive strain means that my section is getting shorter, is getting compressed. The tensile bit means that my section is getting longer, is getting elongated, it's under tension. At the same time, we have the stress, so the stress let's say box for the top bit of concrete, then I have the stress of my bottom steel, and I have the stress from my FRP. And this strain of FD, which was the strain of FRP, as we just discussed it, is a minimum of these two values, either this from the factory or this which relates to the debonding. So the flexural strain happens either in region 1 or region 2. Let's just look at region 1, where the FRP is the main player. So the failure is happening because our strain has reached to this point. At any of these cases, I can calculate the strain in my FRP, which is in tension, the strain in my steel, which is in tension, the strain in my top steel, which is in compression with this formulation, and the strain in my concrete, which is in compression with this formulation. Generally, I have all of the values except X. The X is the neutral axis. And in a couple of slides, we will see how we can calculate this X and the neutral axis. And why do we need that? So far, just focus on the strain. Let's look at mode 2. In this case, we are reaching the maximum concrete compression, so epsilon Cu, ultimate strain of concrete. And as mentioned, based on Eurocode 2, this has a value 0.35%. Then I have the strain of steel in compression, which is calculated like this. I have the strain of steel, which is calculated like this. And I have the strain of FRP, which is over here and is calculated like this. But we don't reach to that strain, so this is a very high strain. Our problem is over here. So we had region 1, FRP failing, region 2, concrete failing. Concrete fails in compression, FRP fails in tension. Now, let's say that, okay, good for us. We have calculated the strain, although we can't calculate them because we don't have the neutral axis. So we cannot compare these together to say, okay, which failure is happening. So we have to solve this problem of how to calculate the neutral axis. again, if you go back to the concept that we were discussing about section analysis in a reinforced concrete, if you remember, there was a trick. We were saying that everything is in equilibrium. So whatever is happening in tension forces should happen in compression forces as well. Otherwise, my section will start walking away. Yeah. So if I look at the stresses now, whatever I have in terms of compressive strength will be equal to the tensile strength. So F of compression will be equal to F of tension. Stress or force can be converted to each other, isn't it? So stress was force divided by area. So if I multiply all of my stresses by their area, I'll get their force. So the first one, which is related to concrete, this area that the force is applied is exactly this area that we just saw in a couple of slides ago. This area, we just simplified it, so we are representing it with a square or a rectangle. So I have the area of this. I know how much is this, how much is this. And then I just multiply it by the strength, which is the maximum stress of my concrete. Isn't this the design concrete strength? The same thing happens with the steel as well. I have the strength or the stress of my steel. I multiply it by area of that steel. The same thing happens with steel 1, which is at the bottom and is carrying the tension. I have its stress and I multiply it by the area of that. The same thing happens with the FRP as well. I have the area of my FRP and I just multiply it by the stress of my FRP. But why are we doing all of these? We are doing all of these to figure out what is the neutral axis. If I figure out the neutral axis, I can simply calculate all of the strains, and then I can compare and see which mode the failure is happening and whether the failure happens yes or no. On the other side, you might ask, what is the stress of my steel? What is the other stress of my steel? Similar to what was the stress of FRP. Strain times the elastic modulus of steel will give you your stress. So always we use these formulations to simplify. The only formula which is a little bit complex over here is concrete, which this relates back to the studies that you have already done on how to analyze a section. But there is an easier way as well. Now, looking at these forces, they all have a distance to a point. Don't you remember moment was force times distance? Moment was force times perpendicular distance. So let's get a moment along this point, meaning this force times its distance, this force times its distance, and this force times its distance to this point. Then this formulation will change to moment equals to force times distance, force times distance, force times distance. Now, this is that moment. So the flexural capacity, which I'm always looking for, do you remember we were saying that the flexural capacity, your resistance should be higher than your applied. I got the applied from my analysis, from my GSA, from ETABS. I was just trying my best to calculate the resistance of my section. This is the resistance. It's just force times the distance to that point, which as you can see, force of concrete times its distance, which is this area of the steel at the top, which is times the stress will give you the force. Again, this force of steel times its distance, which is this watch, and the area times the stress of FRP, which is this force, times D1, which is this distance. Why FS1 is deleted? Because we're getting moment along this point. So the distance over there is 0, so that bit is omitted. If I calculate all of these, I get MRD. All of these values, I already have them. I know what is the area of my steel at the top. I know the area of my steel at the bottom. I know the area of my concrete. I know the area of my FRP. I know the elastic modulus of my steel. I know the elastic modulus of my concrete. I know the elastic modulus of my FRP. So all of these values I know, and I can clearly get the neutral axis as well, and I get all of the sections. So from this formula, if I put it equal to 0, I figure out the neutral axis. Now that I have neutral axis, I take a moment along any point. You can do it along any point that you want, but it's easier to get it along this point, which is the bottom steel. Then that moment will be the resisting moment of your section. Having that moment resisting, you just compare it to the applied load, how many elephants you have. This moment resisting should be higher than the moment that those elephants will produce. As long as this is satisfied, your section is safe, and consider that we have added the FRP at the bottom as well, so we have a new resisting of moment in our section. Imagine if this FRP didn't exist. This bit of the formulation was different, the neutral axis would have been different, and the moment capacity that you get for the section will be for the original section. That was the problem. That moment capacity was lower than my applied, so I added the FRP. The FRP has improved my neutral axis and it has improved my moment capacity. Both of these improvements has increased my resistance. If my resistance is bigger, hopefully it will satisfy my applied load, applied bending moment. Now, the same concept follows in ACI as well. So I'm not going to talk about the ACI, but if you look at the formulations and stuff, are extremely similar to what CNR has considered. So if you're interested, have a look. Now, that was the flexural strength of reinforced concrete. Now let's move on to the shear strength of reinforced concrete. So for the flexural, I got the MRD of my section and I compared it to MED. For the shear, I do the same thing as well. I have the VED from my analysis, from ETABS, SAP 2000, Oasis GSA, Seismostruct, any software that you use. I just have to figure out what is the resistance in terms of shear. This is a good shear crack that you can see in a concrete beam. In this experimental test, we're just applying it at the side, so you can see a proper crack going from the bottom to the top or from the top to the bottom, which is shear. It's not due to the flexural. It's very close to the supports. If you remember, the bending and the flexural is usually away from the support and in the middle because the beam bends. The shear usually is in the sides. Now, the shear again follows the capacity design. So if you can't remember how to calculate the new shear which is applied to your structure, we had to do it a little bit different. If you remember, in capacity design, you design your beam for the bending moment that you have. Then for the shear, in order the capacity design to be applied, you use this new formulation. You get the moments from the previous calculation and you have a new shear. If you can't remember this, please refer back to the courses that we have in Introduction to Seismic Design or Eurocode 8, and you can figure out how to calculate the new shear. I have given the formulations here. It's not very sophisticated. Majority of the softwares actually do this automatically as well. So the shear analysis that you get has already considered these. Now let's imagine that my VED is satisfied and I know what is my VED. We discussed that as always, my resistance should be higher than my applied shear, so then we don't have any problem of shear. In order to have that, the FRP should be applied similar to the struts, the ties, or the shear reinforcement that we put inside the section. If you remember, it goes something like this. So as you can see, my FRPs are going around my sections like this as well. Now sometimes we have angles from 180 degrees all the way to 0, or sometimes we have 90 degrees. Depending on this, the design changes a little bit, but generally the concept is very simple, and it says that the VRD, or the resistance that I have, is a minimum of all of the guys who resist in tension and or all of the guys who resist in compression. So all of the guys who resist in tension are the steel and FRP. So I calculate the VRD of steel using this formula. I calculate the VRD of FRP in the next slide. You will see the formula. I just sum them up. On the other side, I can calculate the VRD of my concrete using a formula. I compare those two values. The minimum will be my VRD. I compare this VRD, which is my resistance shear, with the applied shear. And then if it's higher, perfect. If not, I have to increase the FRP. I have to do some effort. But let's quickly go through this formula as well. Again, similar to the previous formulas, this is related to steel. So as you can see, all of the values which are inside it relate to the steel. For example, ASW is the area of steel stirrups. This stirrup is the same ties, shear reinforcement, straps that you call them, and consider the number of legs. So how many legs they have. This goes back to the design of your reinforced concrete as well. Or the S is the spacing of the steel stirrups. FYWD is the design steel strength of your steel stirrups. As you can see, we are only dealing with the stirrups. This is the shear reinforcement. So those are the important ones. And then some angles that those shear reinforcement are applied inside your section. Sometimes they are angular, some in majority of cases they're straight. So all of these will be a smaller value. So just go through these descriptions. It's not a very sophisticated formula. After passing the resistance of steel for shear capacity, we get to the concrete contribution to shear capacity. Again, a simple formulation. As you can see, majority of the factors relate to your concrete. For example, the depth of your concrete, the width of your concrete, the FCD, which is the design concrete strength, and some angulars, which simply can be figured out just looking at the section. But the new formula is the resistance and the contribution of FRP to shear capacity, which again, as it's just for FRP, the formulation relates to FRP. For example, T of F, thickness of FRP, and FFED, which is the effective design strength of FRP shear reinforcement. I have given the formulation in next slide. It's a kind of a long formulation which shows the design strength of FRP. This is different than that FFD that we used. And some factors as well. Again, as always, depending on how you're applying the FRP and the angle, it really matters. Whether you're applying it in 45 degrees or 90 degrees. Let's look at the FFED, which is a kind of a give or take long formula. So this depends on how the FRP is applied. Imagine this cross section. This is the shear reinforcement that you have, and FRP, as you can see, is only applied like this, like a U-wrap. So depending on whether you're applying it as a U-wrap or you're applying it along the entire length, like this, you're wrapping, completing wrapping, the F-fed has a different formulation. But what is interesting here is that in this F-fed, not only some properties of this height and width plays effect and the angle plays effect, the FFDD that we had from before comes into play as well. What was this? Was the design, the bonding strength of FRP, the bonding starting from the ends. So not FFDD2, this is FFDD, which had its own formulation if you remember. So calculating that comes into this formulation. And if you're wrapping it the entire one, as you can see, it's a massive formulation, which will be a bit different. The U-wrapping and complete wrapping is clearly that U-wrapping will cause a little bit of debonding. That's why the formula of the wrapping has debonding in it as well. For sure, complete wrapping is amazing, but what if your beam has a ceiling on top of it? Can you do complete wrapping? So in majority of cases, unfortunately, we are forced to do shear reinforcement of our beams like U-wrapping. Otherwise, we love it to do the entire thing, but then you will make it a bit sophisticated because you have to cut the slabs and apply the FRP all over it. As always, again, some ACI formulations. If I went a little bit faster during this shear or the flexural calculation, is because when you look at the formula, there's no point of discussing the formula. I have provided some examples, very detailed examples of how to design the flexural and the shear FRP for a beam. Please go through those slides. It's very simple. It's based on a realistic case as well. And you can see that having the MED and VED, which is applied from your analysis, how you can calculate simply the MRD, which is the flexural capacity of your section with the FRP, and VRD, which is the resistance, the shear resistance of your section. If these two are bigger than the applied ones, voila, you have done your proper design. So please refer to Moodle and you will see it. Again, ACI as well, if you see, it's a little bit more complex, but follows exactly the same concepts. Okay, as discussed before, applying FRP on its own is an art. And you really need very expert labor to apply it, and it should be properly supervised to make sure that the quality of this application is to the standard. Otherwise, you will have plenty of debondings and failure issues. Now, generally, FRP comes in different forms. Two of these names, the wet layup and the pre-cured system, are kind of familiar. We discussed these and we discussed how these affect the strain or the strength of your material, for example. But let's look at them. So wet layup is in a situation that you have the fibers. So you have the fiber sheets, you take them on site, and then you soak them with resin on site. So everything is separated, everything will be done on site. The pre-cured one is when you have the sheets, so the fibers and their matrix are mixed. You just bring them on site and you just have to glue them with adhesives to your member. So it's a little bit one step ahead. The pre-preg system is when not only the fibers and the matrices are mixed and proper and ready, the factory has also provided some resin and adhesives at one of the sides of the FRP. So you just have to remove the covering and you just stick it to your member. So this pre-preg system is, let's say, the best one, and it's ready to apply and it's the easiest one. Then there's another form of FRP, which is the FRP reinforcement bars. As you can see over here, their color is a little bit lighter toward white or bronze compared to the normal steel reinforcements. They're not used that much. It's either for research or very sophisticated structures because they're very expensive. So remember, wet layup, pre-cured system, pre-preg system. Depending on any of these, they will have different properties. Some, let's say, comparison between the in-situ curing, which is the wet layup, so everything happens on site, and the prefabricated one, the pre-cured one, which majority of the stuff has happened off-site, is over here. Let's just look at the ease of application. When everything is already prepared, it's simpler to use. And very higher quality is guaranteed. When you have to do everything on site, you have to make sure that the quality control is properly rigorous and you make sure that everything is going fine. But because it's all on site, if you have curves or if you have, let's say, funny shapes, it's more flexible to be applied. Generally, quality control, bad workmanship, unexperienced labor, all of these will cause proper and major issues. So generally you need a proper quality control with someone who really knows how FRP is applied and why and how to design FRP. So if you have those, everything will be fine.